Hello, my name is Daniel Russo. This is homework number 6, problem number 1. We're giving a joint density function f x y, both random variables, xy is equal to b xy when 0 is less than x is less than y is less than or equal to y is less than or equal to 1, 0 otherwise. Now, just to kind of get a little sketch of that in your mind, x, y, y is less, x is less than or equal to y, so that means at one point they equal each other. So y equals x. Just draw that to scale a little better. So y equals x, and x will always be less than y. So when y is, say, 2, x could be anywhere between 0 and 2. So this whole area is kind of where we're looking. So that'll probably be part of our integral of sorts. So the first question is to find b, to make this a valid joint density problem. So it's a pretty simple process. 1 is equal to make it valid, fx y of xy, which is the integral so x ranges from nothing to itself, and y ranges from x to 1. And we're going to integrate dx y. These are not random variables. dxy dy dx. So obviously we can manipulate this a little bit. So x be outside, x here, y there, dy dx. So this will be integral of y is y squared 1/2 1 to x dx dx. So dx0 x multiplied by 1/2 minus 1/2 x squared dx is still equal to 1. 1 is equal to b x 0. Let's actually distribute this. So x over 2 minus x cubed over 2 dx. 1 is equal to b times, so we'll do the integration here, kind of split up if you like, but I'll just do it in one go. It's going to leave you with x squared over 2 minus x cubed over 4 between 1 and 0. 1 is equal to b times 1 squared over 2 minus 1/4 over 4 minus 0. So 1 is equal to b multiplied by 2 over 4, you can switch it up there, to 1 over minus 1 over 4, which is equal to 1/4 I'm working off of I pulled out the 1/2 right here actually to make it a little cleaner. But let's leave it. Let's change this a little bit. So well, if we left the halves in there, then that would be 1/4 and 1/8. 4th and 1/8. And that'd be 1/8, and this would be 2/4 or 2/8. So that would be equal to 1/8. B equal to 1. B is equal to 8 in this case. So on to part B. Find and sketch the marginal density functions fxx and fy of y. So fxx is going to be equal to the integral of the joint density function over the values of x, and x at its least is 0, so x could be 0, and at most is 1. So 8xy dy will equal fully 8x, because you're multiplying with y dy, which is 8x y squared over 2, 1 to x is equal to 8x x 1 squared over 2 minus x squared over 2, which is equal to 8x over 2 minus 8x cubed over 2. When you distribute that through, which could be neater, well, you know, that's going to cancel to 4. 4x common, so 4x 1 minus x squared, and for f of y, then it's something similar, but you know, different as it kind of flipped that all. So y goes from 0, because x could technically be 0, but y doesn't have to be 0. But if x is 0 and y is equal to 0 is equal to x, then 0 would be our limit there. And y is our upper limit, because y can be equal to 1. 8xy dx. So we pull our 8y out. Y to 0. X dx. 8y of y squared over 2, evaluated from y to 0, so 8y multiplied by, sorry, that isn't x, y squared over 2 minus nothing, goose egg there, 0. So 8y cubed over 2. Or 4y cubed. 4y cubed. No x there. Now our part C asks if we could disprove or prove that x and y are independent. And if x and y are independent, fxy would be equal to fx multiplied by fy. So that's for independence. So 8xy would have to be equal to 4x times 1 minus x squared multiplied by 4y cubed. So we can distribute 4xy cubed as a thing throughout the entire thing. So 4x cubed times 4y cubed. So distribute that there. Distribute the 4x to both terms. Distribute the 4y3 to both terms. So 4xy cubed and 4y cubed, 4x cubed. And that is not equal. But let me just reduce a little bit. 2xy is equal to xy cubed minus x cubed y cubed. And in this case, you could even try to equate both sides a little bit. Take an xy out of both terms, you're left with a y squared. And you're left with a x squared y squared. So that's going to cancel out. So unless 2 is equal to y squared minus x squared, don't believe that would be equal, actually. So even factor out that as 1 minus x squared. That would even have roots, but then that's a parabolic function. But essentially it would be a 2 over y squared plus 1 minus x squared. But essentially this function does not equal 8xy. There's too many terms. So I would consider this not independent in this case. So for part D, we're asked to find expected value of x in a variable, expected value of y in a variable, and the expected value of x, y in a variable. So this, simple enough, is equal to the integral of x multiplied by fx, the marginal density, dx. Now we're going to use the same 0 to x, because x's upper limit is y, which could be 1, while 0 is definitely within x's range. This will be 1. X will just be 1 in this case, because that's its max range, and we're trying to find an actual expression. X multiplied by 4x, x minus 1 minus x squared dx. And this will be equal to, well, it's 4x squared minus 4x cubed dx. So distribute that, and we're going to do the whole integration together. So 4x cubed over 3 minus 4x fifth over 5, evaluated from 1 to 0, which will be equal to 4 1 cubed over 3 minus 4 1 to the fifth over 5. Subtract 0, because that's 0. So 4 over 3 minus 4 over 5. If you equate those, that's going to be 15, so 20 over 15 minus 12 over 15. You'll be left with 8 over 15. And our expected value of y is going to be equal to the entire range of y, which is from 0 to y, which is from 0 to 1 really, so y times the fy of y dy, which is equal to, over the entire range, y times 4y cubed dy, so 1 to 0, 4y cubed, that's cubed to the 4th dy, so 4y 5, 1 to 0 is equal to 4, 1, 5 over 5, which is just 4 over 5. Now the expected value of xy is going to be a double integral, integrating over those same boundaries again. X times y times fxy dy dx, which will be 1, 0, 1, 0. So you can't integrate like that, because x is technically your lower limit for y. We want to carry that through to get the accurate answer. So we're going to be kind of drilling down from y to x in this case. So 8xy times 8xy dy and dx. So just dealing with the inside, we can do a little removing of variables. So for all the x variables, x squared, move the 8 to the outside, y times x, and just y squared dy dx. So 8 times 1 x squared, y cubed over 3, evaluate from 1 to x, dx. Go over here, 8, 1, 0, x squared multiplied by x cubed over 3 minus 1 over 3 dx. So we're going to take an 8, take the third out, 1 to 0, x squared, x to the 5th minus x squared dx. This becomes x to the 6th over 6 minus x to the 3rd over 3, evaluated from 1 to 0, 8 thirds, 1 6 minus 1 third minus 0, 8 thirds times 1 6 minus 1 is 2 sixths. Uh-oh, that is not correct. It shouldn't be a negative number. It should be a positive number, I believe. There. So it gives a negative 1 6 times. Let me see, let me try to trace that. should redo some of that and maybe not distribute out so many things. Leave the 8/3 in here. Keep 8 in here with x squared. Then let's it's a little simpler if I actually write it as y cubed minus 1/3 x cubed in this case. And that's 8x squared. So now 8x squared multiplied by x cubed minus 1/3 dx. That's 8 times 1 cubed. Maybe still have to distribute that. 8x cubed squared over 3 is equal to 0. 8x to the 5th and 5th minus squared over 3. So that's 1. Fifth over 8/3. It would be 3 times 8/5 minus 3 times 8/3. We still have 24/5 minus 8. Is slightly less than 5. It's a negative number, and I'm not sure why this isn't working as before. So I worked it out earlier, and I had it. I'm going to try to bring back that logic. I feel like I'm just doing something wrong with distribution. So xy 8y squared. This is going to be 8/3 8y. Move the x in there too. X squared from 1 to x. 1 to 0, that will be 8. Times 1 cubed x squared over 3 minus 8 times x cubed x squared over 3. So that's 8x squared over 3 minus 8 x cubed to the 5th over 3. So that's going to give us the integration of each of those pieces. And you have 8 times 1/3 over 3 times 1/3 minus 6th x to the 5th 6th over 3. Subtracting zeros in there, which is 8/9 minus 8 over 18. I'll do that. Make sure I'm doing my fractions correct here. So it's 4/9. So now it's a positive. It's okay. Well, that's correct. I think I just made a mistake with some fractions there. It leaves us with 4/9. Okay. So maybe taking everything out is too, just keep everything together, it's a little simpler. So that solves that part. Now E is prove or disprove that X, Y are uncorrelated. So for E, uncorrelated means that the expected value of X, Y is equal to the expected value of X multiplied by the expected value of Y. So is 4/9 equal to 4 over 8 over 15 multiplied by 4 over 5. Well, that would have to be, no. That is 8 over 15 multiplied by 4 over 5 is 32 over 75. Not going to be the answer there. Make sure you can see that uncorrelated. It would be correlated if these were equal, but that is not the case. Now for the last part. One of the last parts, F, wants to find the conditional density functions of F, y given x, and F, x given y. And if you sketch them for fixed x, sketch them for fixed y. And you have fixed x here, fixed y here for sketching. So let's first find them both. F of y given x is going to be equal to, breaking out the old conditional probability, is going to be probability that of the fxy, which we already know, divided by the probability of just x, the function that is. So 8xy divided by 4x, 1 minus x squared. So cross that out, cross that to 2. So 2y over 1 minus x squared. And f of x given y, similar format, xy over fy, 8xy divided by y cubed, 4y cubed. So it's 2. Y, so 2, so 2x over y squared. So we have in there to graph those for a fixed, so we're going to graph this one first. So if x were fixed, y given x of 0 it's going to take that and make that just 1. So when y is 0, when x is 0, this is part 2 of question number 1 for homework number 6. My phone ran out of storage space. It's a longer video than expected. So getting back to where we left off, we're going to sketch the conditional density function f of y given x. So when x is 0, it's just the function is going to be equal to 2y. Y is equal to, in this case, function fy given x, which is fixed, is going to be equal to 2y. So 2, it's going to be 1, y is going to be 1, for example. And as the function expands, if y is if x is equal to 1, which is its limit, its max number, then it's easier to think of it as 0.99999, some very small number, or just the variable itself. F of y given x is equal to 2y over 1 minus x squared. So as that approaches 1, you'd be a very tiny number would be the kind of intercept there, but you'd still have a linear function because x is not changing. Just 2y would have a much smaller value. You'd still have a function like this, but it might not be the exact slope, but for all x, for any variable of x, I believe you'd have 1 over 2y over, well, the 2 is, if we just say if y is 1 here, then you have 2 over 1 minus x squared. So if this could be for any value, for if y was changing, then you still have a linear function, essentially. So our second for f of x given y, x, our function is equal to 2x over y squared. And for a fixed y, y was 1, or y was 0, then the function would, for 2, be a very tiny number. Again, be linear in that sense. That would be 4. Let's make it x1 a little neater. So if x is 1, 2 over y squared, kind of be like where that would line up. So as if x was 2, 4 over y squared. But if y were equal to 1, you just have a function, for example, x. X is 1, and it's 2, yada 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 there. So linear functions in this case. but of course it would end at 1. There wouldn't be a 2 because there's boundaries, obviously. 1 being the top. So linear functions essentially between those two, but you kind of have to fix the value for it to understand the exact slope, because y is still varying in this case and x is still varying. Well, x is varying here. X is fixed, these two examples, but if you fix x, you'll have a variety of options. And similar, if you fixed y, you'd have a variety of those sloped answers. And obviously your density should be 1 if you took a derivative under any of those circumstances. And finally, G asks to find the expected values of the conditionals. So the expected value of y given x, so random variable, expected value of y given x, expected value of x given y, and expected value of x given y. Those are random variables in some cases, and these should actually, these two should be equivalent, as well as these two should be equivalent, because the variable y, it's the expected value of that variable, and the random variable y can be mapped on from, y can be mapped onto that. So we understand the random variable y through y, and similar explanation there. So we just defined expected value of y given x to get that value as well. So that would be from x, which is approximately 0, to 1, y multiplied by the conditional y x, y. And we just found yx, so 1 of x, 2y over 1 minus x squared multiplied by y dy. So 2y squared over 1 minus x squared of x dy. So that is y, so 2y cubed, 1/3, still multiplied by 1, divided by 1 over 1 minus x squared, evaluated from 1 to x, which will be equal to 1/3 2 times 1 cubed over 1 minus x squared minus 1/3 times 2 x cubed over 1 minus x squared. So just keep that 1 minus x squared there, it's a little easier to deal with. 1/3, that 2/3 minus, actually, so 2/3 is in both, so 1 minus x cubed. And for expected value of x given y, we're going to have a similar expression, y to 0, 0 being the lowest value of x, y being the top value, x, f of x given y, dx. So that will be y to 0 x times 2x over y squared dx, which is 2x squared over y squared, y0 dx. So evaluating that for x, 2 times 1/2, 1/3 cubed, x cubed over y squared, from y to 0, which will be equal to 2/3 x y cubed over y squared minus 2/3 times 0 cubed over y squared, so it's 0. So we're left with 2/3 y. And that is and that completes the question for number 1, homework number 6. Thanks for watching.